Suzanne observes two light pulses emitted from the same location. So from flash 1 and flash 2, you can see how the distance of those lights are the same, according to her. So we could say that delta flash from the perspective of this pilot is going to be 0 because, well, the distance didn't change from here to there. However, Mark over here, he's going to notice the flash here and then the flash over there. And he noticed that the time between them was 8.5 microseconds, and Suzanne noticed that the time was only 3.5 microseconds. From this, we know, well, proper time tells us, hey, this is the person driving over here, right? Because they're measuring this, and this is the observer over here. So this thing must be the thing moving. But we're asked to figure out, well, this is the velocity of Mark with respect to Suzanne. Yeah, that's probably because, you know, either perspective works. The velocity of the train going in this direction from a still observer's perspective, it's kind of like saying, okay, well, the train could be still, and then this guy could actually be the guy just moving really fast over here. Velocity of the observer versus a still train. So either one of those works. Now we're just trying to figure out what that velocity is, so let's just compare these two times. Since we know that the delta TO, I'm going to get the square root of 1 minus v squared over c squared, that's just going to be equal to the delta TP. And so we could plug in these numbers. We'll get 8.5 microseconds, square root of 1 minus the v squared over c squared is going to be equal to 3.5 microseconds. So we could try to rearrange this, put 3.5 over 8.5. Let's get this squared, so that'll equal 1 minus v squared over c squared. From here, let's just take 1 minus 3.5 over 8.5 squared is going to be equal to the v squared over c squared. We'll multiply everything by c squared, getting rid of it on that side, and then we can square root it. So we'll figure out what the v is. So we could say 3e to the 8 squared, and multiply that by 1 minus 3.5 over 8.5, square that, and we'll just square root that, and we'll divide it by 3e to the 8, so that way we can get a fraction of c. Just say v equals 0.911c. Now let's try to find the distance between those flashes from Mark's perspective. So we can use that the change of some moving flashes from the observer's perspective is going to be multiplied by our 1 minus v squared over c squared. And that will be equal to the delta of the pilot's perspective in terms of the light, which in this case is just 0, so we can kind of just ignore that. But then we're going to add the v of the train times the pilot's perceived time, which is TP. So this is just simply the Lorentz transformation, where we're taking the perspective of the observer and we're comparing it to the perspective of the pilot of this moving train here. Now, from the perspective of the pilot, this flash is going to happen at the same point, so there's no change in position here, so we can get rid of that. So this will simplify down to something like the distance between those flashes from the observer's perspective by this little factor here is going to be equal to the v of the train times this TP, which we've already found to be the time of the observer, times, again, that little factor here. So we can actually get rid of these factors, and then we'll be left with the distance observed is actually just the velocity of the train times this observed time. So let's figure that out. We still have our velocity from before. Let's make sure to multiply that by c. And then we'll use the time observed, which is 8.5 microseconds. And so now we'll find that the flash distance here, was observed by Mark, is simply going to be 23.8 meters.